So, again, a good morning, ladies and gentlemen. Thank you very much, Pavel, for your introduction. As was mentioned, my name is Petr Konas, and I am a head of R&D at SVS FEM, and I am doing simulations almost 30 years, mainly with respect to multiphysical and multi-scale problems. I was asked by Professor Mañas to create some short overview about tools and utilization of numerical simulations. So today we should shortly talk about introduction to numerical world, mainly according to the current significance of such methods and according to the future of such tools in a real and engineering point of view. I wouldn't like to describe any equations nor the difficult theory today, but I would like to show you what you can expect if you will focus on this type of engineering in your future career, and what is the nowadays utilization of simulations around you. If you will have any question, please write it down to the chat, and I will try to answer all questions which I can at the end of the presentation. Well, so if you can see my screen at the beginning, let us assume you are engineers and you would like to know what will be the behavior of your construction. And it can be anything. For example, the bridge, mining harvester, Apple Watch, nuclear power plant, or nice, unique, smart and green car. You have two crucial choices. First one, you can create your construction and you can test it if your design is correct or not. If you plan to build some simple beam, you have small chance that after several trials you will find some design which will be still innovative and interesting as for you, as for investor who will invest to your business and to your product. But the more complex solution you want to create, the more impossible seems to go this way. Usually, you will need really good budget and you will need a crowd of other engineers and people which have to assist you with testing, prototyping, validation, accounting, and so on. So, nowadays, you will choose the second approach very often. This way is virtual prototyping of your design and testing it in virtual reality. Such virtual reality has to be the most similar to the real world as possible. Only such way you will be able to exclude the wrong prototypes and incorrect responses very fast and relatively cheap. To go this way, you will need trustful and sometimes also foolproof tools which are able to create such virtualization of the world. In other words, you will need powerful solvers of numerical tasks, and having great solvers is the foundation of your vision, but to truly meet design demands, to truly predict with confidence, this solver must be able to simulate to complete product and real-world behavior. As products become more complex, seldom is complete and confident validation achieved with the consideration of one physics. Instead, all physical phenomena must be considered as they act together with each other in some comprehensive multiphysics environment rather than in isolation of each other. Simulating the real-life behavior of your product in its real-life environment is what we call a virtual prototype. It's about reducing uncertainty, reducing the number of approximations used in simulating the performance of system in its real-world environment. So, back to the idea of the car. You can virtualize, for example, battery, engine, fan, etc. But it will be still one or more separate components. Only when all such components are working together, only when the whole complex is working as one identity, only then we can speak about the car. And only then our simulation can be approaching the real world in the complex view as it's needed and as it's required today. One of the most crucial parts, as in the real world, as in a world virtual, is description of the material. Today you need the material in CAD, because without material you are not able to create the bill list, and without the bill you have zero chance to continue any other way. Also, you need material in CAE, it means in a world of simulation, because of absence of material means the absence of the physics, and description of your design can be interesting and maybe also be working on some planet or some universe, but not on the Earth and not in our universe. And this could be, of course, a little bit problem. Of course, if you created some CAD model and CAE simulation, you should manufacture your design very often by some chem process. And again, without material, you are not able to process the rough ingot, and your manufacturing will be at least full of waste. Finally, nowadays materials are usually complex, smart and green. Without knowledge of materials, you are without any chance to create any innovative solution. Materials information matters because there are these four fundamental factors to think about when making a product. Images show how we thought about these in the pre-digital era. Today, we usually don't use a drawing board for shape, we use a CAD. In the same way, the common material list is the same archaism and not sufficient in today's world of virtual prototyping. Today, you need information not only about family of material, if it's metal, polymer, wood or something else. You also need to fulfill difficult requirements given by standards in individual industry fields. For example, in healthcare industry, you are really very limited which materials in what environments for what purpose can be used, and similarly in aero, military defense, space and other industries. Nowadays you need not only the price and young module of the material, you also need an emission footprint, biology compatibility, electromagnetic compatibility, nature risks and many others. In other words, you need very complex tools which are able to show you the correct material which can be used in a correct way and ideally in the whole virtual environment regardless what application or code you are using. To interrogate all such data, it's very important to include a range of visualization, screening, comparison and reporting tools to help you identify optimal materials, compare them against baseline material or your company's preferred materials. You can then create material cards ready for your CAD or CAE simulation and reports that document the material selection process. Also, you can find similar materials which can replace your chosen material, and you can dynamically adapt your list of materials according to changing external requirements, for example, small change in function, constraints, objectives, and so on. By these core tools, you also need to have some tool that incorporates a part cost estimator and models that predict the performance of hybrid materials and structures such as sandwich panels and multi-layer structures, and also some eco-audit tool that estimates the carbon footprint and energy usage of products. These allow what-if scenarios to be quickly tested out and validated in the early stages of design. In such way, you can prepare valid inputs to the following numerical simulation. Okay, You have an idea, you have a material, but what next? Can I simulate? And how to create so-called virtual prototype? Well, there are many approximation methods which can be used for some kind of virtualization. If your quadratic function behavior of your system, it's also some kind of very primitive virtual prototype. Nevertheless, our common description of the physical world is based usually on partial differential equations, and we are looking for methods which allow us to solve such type of equations. Also, usually need to solve more complex geometries than a simple cube or rectangle. So we need some discretization techniques which simplifies our studied domains. And don't forget the way how domains interact with the surrounding environment. They also need to be described by some boundaries and initial conditions, and so on and so on. In other words, we can say that you can study numerical math the whole life, and you will teach a new method and new technology for numerical simulation every day. Our today world of knowledge is so complex that there is nobody who can even candidate to be the wise man who knows everything which corresponds with numerical simulation. The reason is very simple. The world of simulation is on the edge of many scientific fields. You can know something from math, physics, structure or civil engineering, but it's also about IT, programming, HPC. Many problems can be solved by biology-inspired approach, and many boundary conditions relies on social and economic metrics. Does it mean that there's no sense to study such field? I think definitely no. It means that there is a large amount of subfields which can be interesting just for you, and where you can reveal really revolutionary breakpoints. And it also means that it's very wise to use appropriate tools in fields where you are not an expert, but where you need some information. Well, look on your table, look on your hands or pockets. You have probably a cell phone, maybe some smartwatches or smartband. Definitely you are sitting in front of the notebook. Well, isn't it foolish to have so many tools to know what is the time? Definitely yes, you can be totally without any of such tool, and you will be able to get an information about the time. So why we are using these tools? All of them are computers and all of them are almost redundant. So why we have so many computers around? Yeah, of course it's cool, but why even your or my grandma probably already buy the smartphone? The reason is simple. It satisfies many of our changing and dynamic requirements. It's not just about the time. It's about calendar, video meetings, games, and so on. And as more complicated and more difficult requirements we have, as more sophisticated tool or hardware we need. And as it is so stupid to play Far Cry on your watches, the same way it's stupid to measure your swimming activity in pool by HPC cluster. Same optic, we should see also nowadays tools for numerical simulations. There are many. But usually you should use the right one in the right situation. Many of my colleagues are saying, don't use this or another tool. It's not accurate, it's a black box, and so on. But why they are using pen and paper in Word, where we can be sure that it's not linear and cannot be described on a simple paper sheet? Is the pen and from this view? Yes and no. It depends on what you need. The measure is goal, what you need to achieve. If the goal is to know quickly the probable response of your structure, then it's nonsense to use complicated tools where studying only of the environment takes several years. In the same way, if you need the precise answer of fatigue life in anisoelastoplastic response of engine, then it's not so wise to use, for example, MATLAB. Here you can see the most common tools in the table, and of course it's not the full list. The message of the table is try to define your goal and choose the most appropriate tool. And choose carefully. You are looking for tools which can be combined. Even you are solving the structural task about strength, for example, it's highly probable today that very soon you will have to solve the same geometry according to the CFD, Electromagnetics, or something similar. Because of the real world doesn't consist just from the one physics field. Usually there are more of them, and very often they are in synergy and must be solved by tightly coupled way. You are looking also for well-documented tool where the information don't need to be digit, but where you can find useful help for your task. And it's important to say that just know you have real unique chance to access a lot of knowledge and tools free of charge, and this chance will be probably only one in your life. I know about these ones on this slide, which are available on your university, but try to look around and you will probably find more of them, which can be interesting and which can be helpful for you. From my perspective, it's also very important for you to create strong and reliable professional community just now, because only experts in different fields can help you in a future and a very complicated world where many specializations will disappear and many new will arise. So try to participate in student communities and try to be active. Only such proactive way you will be able to solve the most complicated problems in the future. And also don't rely just on scripts and lectures on the university. They are the basic, what you will need. But try to utilize many platforms which are tightly focused for specific professional topics. They are also very often free of charge for the student, but they are also created in tight cooperation with industry leaders and professionals from the industry, which forms the most interesting questions and problems for numerical tasks today. One of such very promising area is artificial intelligence. Nowadays approach of AI is very heavy style. You need tons of data, you need tons of classifications, you need a lot of specialized networks. It's time intensive, resource intensive, and usually it provides only tightly usable solution. But there is a fantastic area in combination of AI and numerical simulation of the real world. Numerical simulations are able to provide reliable data very quickly, and you don't need to build the structure physically. This way, you can train and teach neural networks much more wisely, so they can be very robust and prepared to the world outside. We have a unique time because this field is establishing just now, and in the future we will be able to solve problems which are inverse, discontinuous, crossing from atomic to space scale. So we will be able to solve tasks which are unsolvable today, but solvable maybe with help of AI. It's a wonderful world, and it's perfect opportunity to be part of it. And you have many chances to use such opportunity on almost arbitrary level. Here you can see, for example, where you can find simulations in aerospace, defense. On the left, you have industry segments, and on the top of the slide, you have systems which are usually solved. The same list of utilization or simulations we can create for medical industry, where mainly nowadays the simulations play the crucial way to keep the life better and long. Also high-tech, which was very often the first who use the simulations and which will provide also in the future many problems which are solvable just by numerics. On the contrary, even such ground industry field as oil and gas processing can provide many interesting problems literally from well to pump. For example, drilling, flow assurance, multi-body hydrodynamic, impact, blast, fire, safety, piping, refining, fuel formation, electronic sensors, and many others. And we shouldn't forget on rotating machinery solutions, which can help us in propellers, compressors, expanders, fans, motors, and so on. In all such fields, you can find simulations just now, and most of them cannot be competitive or even exist without first-class simulation tools. Just for example, how such virtual prototyping can look like, take a glance at the following slide. Here, we would like to simulate a complete product system to optimize the architecture and ensure that the overall system requirements are achieved before physical testing. You can see that for such goal, many systems has to be combined. For example, the embedded logic from some IoT system which drives the electromagnetic system, together with hydraulic system. Problem where there is no space for wasting heat from resistive heating, no space for acoustic noise, no space for failures due to an inappropriate cooling, powering, loading, moving, and so on. And if you have sufficiently general tool for system simulations, which allows to combine different physics with system response, you have the chance to solve the similar way the washing machine on the top left, or the smart electric car driven by artificial intelligence in the middle of the slide. There is another case where you have description of physics. You have also several embedded systems, but you want to create an algorithm or application which will drive the whole system. Such application has to be without any bug. It has to have several duplicities of system when some control will fail and satisfies all required standards given by aerospace industry. Such way, we can create a new Eurocopter which will be adapted in many situations even before it will be created and assembled physically. Such approach increases ability to manage system complexity by providing multiple perspectives. It improves product quality and accelerates the overall development cycle. And now try to imagine some product which must satisfy requirements across a wide range of industries. It must be in the form of software, for example, where individual components of such software is driven by physical models. You need certified solution which is able to provide verification and optimization of code with common software development cycle from idea to update packages with maximum safety and defined life cycle. Only correlation of your code with ever-changing hardware standard is a very difficult task. Nevertheless, combination of all such requirements satisfies only several platforms in the world at all. But current industry has no time for development in some quiet corner. In a real world, in any smart factory, you have thousands of robots, sensors, data conversions, and events which has to be included in your simulation. In other words, if you want to create a digital twin of some product, you have to create digital twin of the whole process, including the project management, marketing, sales, stock, purchase, or personal department. You need a cloud where all data are streamed, analyzed, and processed, and send to your department of R&D for design of a new product or lowering the expenses at least. And from this reason, you need professional PLM system which combines the common administrative CRM systems with your CAD and all other systems. When you have such complex platform which allows to share individual projects and which allows to combine results from solution of specific physical problems, you can have the luxury to divide the complex problems into individual tasks and solve them separately. As for example, you can see on this picture where the project is to develop a new Airbus, but this specific task is focused only on simulation of landing gear in landing or taking off. As you can see, again, the solid structure of landing gear together with kinematics and hydraulic system, which is driven by electromagnetic system, can be solved. By such, you can create parametric analysis where parameters can be as deterministic as stochastic, and you can compute the optimization task where multiple objective goals must be achieved. As you can see on this slide, for example, where you have detailed physical model of electromotors in drone, but you need to drive the velocity and acceleration of motors according to the climate, position, altitude, and many other. This way you can create an autonomous system of driving which can react on various loads and climate conditions, and which will be able to satisfy the primary goal, which can be the, for example, the parcel delivery. If you have precise, systematic simulation, then it's up to your choice how detailed will be the physical description of the component. And you can choose the approximation method, or you can combine several methods into some holistic and hybrid solution, where the optimal methods are used for specific subdomains, boundaries, or conditions. One of such a robust method is discrete element method, where the domain can be solved on Lagrange or Euler domain with simplification to individual particles and its response. This approach is very useful when you need to simulate thousands or billions particles which interact and can break or interconnect. Then you can ask what is the varying of the tools, what are the reaction forces, or what is the stable pole angle, for example. One of the latest interesting implemented method is also moving particle simulation method, which is very similar to previous, but it's focused more to hydrodynamics. By this tool, you can solve the, for example, lubrication, splashing, sloshing, soiling, wetting, and so on. Even if you want to know what will be the impact of tsunami wave on some inhabited coast, you can predict the height, strength, and other effects which allow you to focus on optimal rescue or evacuation plans and so on. Maybe we can wait just a moment, and you will see that even so complicated geometry and so complicated physical model can be included and modeled just now, and can include many details. And it doesn't matter on the large or the subdomain. Of course, very complicated physics can be included, for example here, a gearbox which is lubricating. So I think from my point of view it's fascinating, because several years ago simulation of such problems was really impossible. Okay. Such simulation tools enable engineers to simulate also the entire additive manufacturing process chain, including topological optimization, part validation, build setup, support generation, build fail prevention, microstructure prediction, and more. True design for additive manufacturing requires a knowledge of all of these aspects of additive manufacturing production to ensure a successful, high-performance, accurate part as an outcome, without the need for expensive and time-consuming trial and error optimization. A little bit challenging remains models where several physics are less or more tightly coupled. A typical example is fluid-solid interaction, where you need to take the pressure of fluid flow as an impact to structure and deformation of structure as an impact on flowing medium. Accurate capturing interplay of these effects is key for development of many products from various industries. As you can see there, for example, large reflection aeroelasticity, fluttering, smooth aortic valve placement in healthcare, performance in extreme environments, for example, space flights, contained nuclear fusion, high-performance waterbox design, and so on. And very often you have to include also the influence of heat transfer as conduction, convection, or radiation. Very often all of them. Typically when you solve the exhaust system, storage tank, or gas turbine blade, you must combine all of them to get an appropriate result. Without precise results, which include the temperature deformation and precise convective heat transfer from flowing air outer and sloshing fluid inner, it's usually impossible to design any innovative solution. And we can continue with such combinations where, for example, structural, thermal, and electromagnetic fields are combined, typically by various PCB boards and electrosystems, where electromagnetic field is holder of resistive losses leading to temperature distribution and temperature deformation. As you can see, you can find utilization of such kind of problems across different industry fields, from medical, high-tech, or civil engineering. Of course, challenge even today can be combination of 4 and more physical fields together. Such kind of solution is typical by electromagnetic devices where the surrounding fluid effects and the rate of heat transfer must be taken into account. It's typical mainly for prediction of electric motor performance or prediction of material failure in aircraft. Also, acoustic effects minimization can be important for electric motors or electric generators and can be solved in coupled manner with the influence of other fields. If you are able to describe the base physical response, you can try to compute also derived variables. It's very often durability or product life. And it can be simple for simple geometry. Yeah, but when you combine coupled physical loads together with large and complex model, it's difficult to find the weakest part which will lead to damage or to the failure at least. For example, when you are solving the wind turbines, you have strongly coupled tasks with structural, thermal, fluid, electromagnetics effects, and revealing of the fatigue life and prediction of product life can be really a challenge. And the question can be more complicated when you try to describe precisely the inner structure of the blades. There is sophisticated, non-linear structurized composite which provides high strength, low weight, but which generates also hotspots, local effects, fast phase changes, delamination, and new types of instabilities, and so on. Of course, rotor dynamics of wind turbines is a relatively simple problem, but what will happen if you need to describe very complex motion where inertial effects and history of path can influence the whole system. Try to imagine, for example, the Swiss watches with many springs, gears, joints and other mechanisms, or car's wheeling carrying system, when you need to compute the fatigue and deformation effects with plastic response. Also, very common is kinematics of autonomous robots, which is adaptive according to the surrounding environment. Up to now, we demonstrated mostly implicit methods of numerical simulation, which is suitable mainly for slow and nonlinear effects. But what about very fast effects? Well, just today, no problem. You can simulate explosion, penetration, fragmentation, together with forming, rolling, sealing, contacting, and many others. Usually you are using explicit methods for such tasks. And we could continue such way several hours and probably several days, at the most probably several years, if you want to go more deeply into the wonderful world of numerical simulations. But I'm afraid my time is over. So I hope you will find at least one or two pictures interesting for you, for your future and for your future work. And maybe we will meet on any other event in exclusive community of simulation engineers. So thank you very much for your attention and see you again, not only in the virtual world. And if you have any questions, we can try to solve it.